Hello, and thanks for joining us today as we present to you automated ORP for wastewater. We believe that we are on the cutting edge of an untapped process control system for wastewater that could very well revolutionize the way we think about and treat wastewater. In this presentation, we'd like to accomplish a few things. First, to show you the many benefits of using an automated ORP system. Next, to leave you with a firm understanding of how and why the process works so well. And lastly, to show you some of the proof in the pudding, so to speak, with some case study plants that are currently in operation and meeting or exceeding their effluent requirement. So sit back and get ready for automated ORP for wastewater. The use of an automated ORP system is simply stated as a controlling system that effectively creates and maintains the proper environment needed for nitrification and denitrification. The ORP system automatically responds to changes in flow, loading, and temperature without operator assistance. Once the site parameters are tuned, no further modification is necessary other than minor seasonal changes or changes to accommodate a failed piece of equipment. Using ORP is the most effective way in maintaining and controlling the nitrogen levels required by the governing entities. No other type of automated system continually monitors and adjusts the treatment process. Additionally, ORP is also a very good tool that can be used to effectively create the proper environment for phosphorus release and removal as the nitrification cycle is started. The use of biological phosphorus removal will help cut down, if not eliminate altogether, the need for chemical addition. And, as an added bonus, the use of ORP reduces the amount of energy used for aeration by using only the air needed to meet the treatment needs. Energy savings are realized as large blowers remain at rest during periods of unnecessary aeration. Biological nitrification, denitrification, phosphorus removal, and energy savings? So just how do we realize all of these benefits from an automated ORP for wastewater system? Well, we start with an existing activated sludge or SBR treatment facility. As influent enters the basin, activated sludge provides the bacteria or biomass necessary for the biological reactions that result from the manipulation of the oxic, anoxic, and anaerobic phases. The changes between the phases are automated based on real-time DO and ORP readings. Now, as we know, the nitrogen cycle is critical to all living organisms that exist on the planet. Wastewater treatment plants play a critical role in reintroducing nitrogen back into the cycle with a limited environmental impact. High levels of nitrogen entering natural waterways can result in toxic conditions for wildlife, dissolved oxygen depletion, and excessive algae growth, all harmful to local plant, animal, and human populations. Nitrogen enters wastewater through various pathways. The most abundant contributor of nitrogen in typical municipal wastewater is urea. You got it, urine. Other contributors of nitrogen are food processing waste, chemical cleaning agents, and many other industrial components. Let's take a closer look at each of these important steps in the nitrogen removal process and how they relate to the stages in the automated ORP process. As a natural reaction in an aqueous solution, or in water, the vast majority of organic nitrogen immediately hydrolyzes into ammonia. Due to the pH levels of typical wastewater, most of the ammonia then automatically converts to the ionic form ammonium. No bacteria is necessary for this conversion, it just happens. The first step in the nitrogen removal process is known as the oxic stage. High-power blowers add sufficient oxygen to the mixture to obtain a proper DO level. When DO levels are high, the ORP increases and the system turns the blowers off. In this oxygen-rich environment, nitrification occurs, converting ammonium to nitrite and then nitrite to nitrate. It's important to note that if nitrifiers aren't allowed enough time to thrive, you run the risk of accidentally wasting them out of the system and entirely losing your nitrification. The real-time readings performed by an automated ORP system help to keep this phase in check. Once a healthy population of nitrifiers has developed, the first stage, performed largely by a group of bugs known as ammonia oxidizers, will take the ammonium and DO and convert it into acid, water, nitrite, and energy. The water produced is absorbed into the system, the nitrite moves on to the next step, and the energy is used by the bacteria to grow and multiply. In the second step, a group of bugs known as nitrite oxidizers takes that nitrite and more DO and converts it into nitrate and energy. Nitrification is a very oxygen-hungry process. As a comparison, in order to remove 1 pound of BOD, 1.2 pounds of oxygen are required. However, to reduce 1 pound of ammonia to nitrate, 4.6 pounds of oxygen are required. Since getting DO into wastewater is a very energy-intensive process, an automated ORP for wastewater system will benefit a treatment plant's electrical bill by exactly controlling the aeration speed and time, and effectively eliminating over-aeration. Over-aerating does nothing to improve the process, and it really is essentially flushing money down the toilet. The final step in completely removing nitrogen from the system is called denitrification. Once the blowers are disengaged, the process begins to enter the anoxic stage, and DO drops to an undetectable amount. During this time, denitrification is performed by specialized heterotrophic bacteria. Now these guys require some pretty specific conditions to perform this step. First of all, they need some food, or BOD. In order to oxidize that food, they need oxygen. Their easiest and first choice for oxygen is DO, but when no DO is present, they must look to an alternative source, nitrate. Fortunately, these specialists have the ability to strip the oxygen from nitrate molecules to satisfy their needs. This critical environment, where DO is not present but nitrates are, is referred to as anoxic and is absolutely required for denitrification. These bugs take the BOD and nitrate to produce energy, base, and nitrogen gas. The nitrogen gas floats in tiny bubbles to the surface and into the atmosphere. When there no longer remains any free oxygen, or DO, the basin enters the anaerobic stage, and bacteria become stressed and begin to release orthophosphate. As the ORP level continues to fall, the blowers are initiated once again, introducing fresh oxygen into the basin. This begins to bring the basin back into an oxic stage, and the stressed bacteria reabsorb the phosphorus. However, because the bacteria are stressed, they now absorb phosphorus at 2 to 3 times the normal rate. Phosphorus is then removed when the sludge is wasted. Three years ago, CNC Instrumentation and Controls was asked to review any published information on the use of ORP in the wastewater field and to develop an automated control system that had the ability to create the proper treatment environment to consistently accomplish nitrification and denitrification. Up until this time, the only type of automated control we typically used with small wastewater treatment facilities was the use of a dissolved oxygen transmitter that controlled the speed of a blower by means of a variable frequency drive. This application is a fairly common method and does limit the common problems of over-aeration, but it does not help much with denitrification. This certainly is an effective system, and it usually works as designed, as long as the design flow, design loading, and minimum infiltration exists within the collection system. Fast forward to today, CNC Instrumentation and Controls has developed an automated control system combining the use of ORP and dissolved oxygen levels to control treatment, aeration, and mixing to provide a proper environment for the biological process to take place. The development was first applied to a sequencing batch reactor and later adapted to a flow-through extended aeration plant. Both applications have proven to provide excellent results. Currently, not only are both plants meeting the permitted discharge level of total inorganic nitrogens, but in most cases, they're consistently producing levels as low as 0.5 to 2 parts per million TIN. Furthermore, an unexpected green benefit of this application has been the energy savings. For example, an SBR treatment plant could expect to see a 10 to 15% decrease in energy use, while an extended aeration plant may see as much as 20 to 40% reduction of energy consumption. Automated ORP for wastewater is an excellent way for owners to go green and save green. In the fall of 2010, CNC Instrumentation started a pilot study at a local dual-unit SBR treatment plant that was struggling and very frequently not meeting their discharge permit. The plant was a good choice due to its close location and a newly replaced PLC. After the initial installation of DO and ORP transmitters to each unit and some additional programming, the lesson soon began, and before long we had a list of problems to consider. The positive note to the study was that very early on it was clear by lab and field testing that the application was very effective. The problem was to maintain a good quality effluent. While the initial results were encouraging, we realized that because of the simple nature of an SBR plant, we could hold captive the treatment batch until the results we wanted were achieved. We quickly discovered that programming changes were needed with more realistic ORP target values and treatment times. These changes enabled us to maintain an acceptable level in the EQ tank. We remained on site for a few weeks. Settings were adjusted according to lab and field test results to consistently achieve the best quality effluent possible. However, several equipment problems were discovered during these studies that eventually had to be addressed by the owner. The motive pumps used for both mixing and aeration were consistently plugging. Once plugged, any success at a quality effluent was impossible. The pumps were eventually replaced with grinder pumps, and we were on our way. The very first application taught us that a newly applied ORP control system will bring to light any and all equipment shortcomings. Overall, the pilot study was a success. The owner purchased the installed equipment and is currently meeting their discharge permit. After a very successful installation at the SBR treatment facility, we were ready to apply our new system control package to an extended aeration flow-through plant. This presented a few problems right at the start with the design use of the blowers. Not only were the blowers used for aeration, but they also supplied all the mixing in the treatment tank and supply air for the airlift return pumps. The site had 3 10-horsepower blowers, along with 2 smaller blowers, all of which were connected to a common air header. We weren't sure if the smaller blowers were intended to be used in cold weather or what their intended purpose was. The smaller blowers were separated from the common header and used for the airlift sludge return pumps only. Our thought was to use the aeration tank to provide most of our treatment and then use the existing anoxic tank as a polished denitrification stage. After reviewing the site drawings and based on average influent flow, there was more than enough detention time to continually cycle the tank between nitrification and denitrification. A floating mixer was installed in the tank to provide continuous biomass mixing while the blowers were turned off during the denitrification cycle. The ORP and dissolved oxygen probes were installed as close as possible to the tank discharge pipe to get an average sample of the processed water as it was leaving the tank. Each blower was supplied with a PLC-controlled VFD to maintain the preset DO level for the nitrification cycle until the ORP target value was reached. Once the equipment was installed and online, we soon learned why existing operation of the plant was requiring the use of all 3 blowers. We were unable to raise the dissolved oxygen level to 0.5 parts per million by running only 1 blower. It actually required all 3 blowers to raise the DO level enough to achieve any nitrification. Upon further investigation, we discovered that most of the diffuser pipes were either missing or had large holes in them. This gave the surface impression of a working aeration system, when in reality, it wasn't really working at all. In short, the diffusers would have been a major expense to replace. However, even with the damaged diffusers, CNC's automated ORP system very quickly brought this facility into compliance and saved the owner money many times over. One of our early installations of an ORP system occurred at a private wastewater treatment facility. The owner was faced with 2 expensive options. One was the connection to a nearby municipal system at a cost of $1.4 million. The other was replacing the existing plant with a new treatment plant estimated at a cost of about $1 million. CNC was contacted through the owner's engineer to review the plant's condition and to design an ORP system that would bring the plant's effluent nitrogen levels down to meet the current permit level. the proposed ORP installation was to require the following equipment alterations and/or additions. Total upgrade of the existing electrical system to meet current code and provide a dependable electrical service. Build and install a custom PLC-based control panel inside the blower building. Isolate the fourth aeration blower and discharge piping. This would provide a continuous air supply for the sludge return pumps from the clarifier. Install 2 submersible mixers in the existing treatment tanks, and install ORP and dissolved oxygen sensors at the aeration tank. The overall cost of the entire ORP overhaul was less than $70,000, and no additional construction was needed to bring the plant effluent into compliance. Today, this plant is currently meeting its required discharge limits and saving a fair amount of money on energy bills at the same time. While the investment of this system was sizable, it was a welcome solution in lieu of the other options available to the owner. It's clear that in this case, automated ORP for wastewater saved the owner a minimum of $900,000 over the cost of new construction. We want to thank you again for allowing us to present to you today. Hopefully, we've convinced you that automated ORP for wastewater can be a viable and affordable solution to your non-compliance issues. Whether you're a facility owner, an engineer, or a DEQ enforcement official, we are ready to put a plan of action together for your most challenging sites. With several system installations under our belt, each of which presenting its own difficulties to overcome, we have acquired an extensive ORP knowledge base, and we're ready to put it to work planning and designing your next project. We've experienced and overcome some unique issues, and in all cases, the use of an automated ORP system provided an effective means of controlling the treatment process and bringing the facilities into compliance. Installing an automated ORP system is more than just dropping a sensor in a treatment tank and connecting it to a PLC, and it's just a small part of a complete operating system. CNC Instrumentation and Control is fit to the task of designing and integrating an automated ORP system for your application. While the investment can be sizable, it's still a relatively inexpensive means to achieve compliance, go green, and to save money on energy bills all at the same time. Look at it this way. If you add those savings up over the years, eventually the system could actually pay for itself. Thanks for joining us.